Hello and welcome to this lesson on covalent bonding. In today's lesson, we will understand the formation of covalent bonds between atoms. Then we will recognize the strength of covalent bonds and how they contribute to the properties of substances. We have previously covered ionic and metallic bonds. Building upon this foundation, we'll introduce a third type of bond, covalent bonds. To understand the formation of covalent bonds, let's start with the basics. Covalent bonds are formed when atoms share pairs of electrons to achieve a stable electron configuration. Typically, covalent bonds occur between non-metal atoms. Non-metals tend to have a stronger attraction for electrons compared to metals. When two non-metal atoms come close together, neither atom fully donates or accepts electrons. Instead, they share electrons to fill their outer shells. Let's consider the molecule of hydrogen as our starting example. A hydrogen atom has one electron, and it needs one more to achieve the stable configuration of helium, which has two electrons. When two hydrogen atoms come together, they each contribute one electron to a shared pair. This shared pair of electrons forms a single covalent bond, resulting in a stable H2 molecule with each hydrogen atom having a full outer shell of two electrons. In a covalent bond, the shared electron pair is located in the region between the two atomic nuclei. The negative charge of the electrons is attracted to both positively charged nuclei, creating a strong attraction that holds the atoms together. This electrostatic attraction is the key reason why covalent bonds are strong. Covalent bonds can involve more than one pair of shared electrons. For instance, let us examine oxygen gas, O2. Each oxygen atom has 6 electrons in its valence shell and needs 2 more to achieve a stable configuration. By sharing 2 pairs of electrons, each oxygen atom can achieve this configuration, forming a double covalent bond. We have a similar situation with nitrogen gas, N2. Nitrogen atoms have 5 electrons in their valence shells and need 3 more to achieve a stable configuration. By sharing 3 pairs of electrons, each nitrogen atom can achieve this configuration, forming a triple bond. The strength of a covalent bond is linked to the number of shared electron pairs. Double and triple bonds are stronger than single covalent bonds because they involve more shared electrons, which increase the electrostatic attraction between the electrons and positive nuclei. Let's look at a few examples to illustrate covalent compounds. In a water molecule, each of the 2 hydrogen atoms shares 1 pair of electrons with the oxygen atom. Hence, each hydrogen atom forms a single covalent bond with oxygen. This sharing of electrons allows the oxygen atom to complete its valence shell with 8 electrons and each hydrogen atom to have 2 electrons in its valence shell, resulting in a stable structure. In a carbon dioxide molecule, the carbon atom shares 2 pairs of electrons with each oxygen atom, forming 2 double bonds. This allows a carbon atom to achieve a stable configuration with 8 electrons in its valence shell, and each oxygen atom to also complete its valence shell with 8 electrons. In a methane molecule, the carbon atom shares 1 pair of electrons with each of the 4 hydrogen atoms, forming 4 single covalent bonds. This sharing allows the carbon atom to complete its valence shell with 8 electrons and each hydrogen atom to have 2 electrons in its valence shell. The previous examples are what we refer to as simple covalent substances. Those consist of a few atoms bonded tightly together by covalent bonds, forming discrete units. These molecules have specific chemical formulas that indicate which atoms are present and in what quantities. Besides these simple molecules, covalent bonding can also form giant structures and polymers. Giant covalent structures, such as diamond and graphite, consist of a vast network of atoms bonded together by covalent bonds, giving them unique properties like extreme hardness or electrical conductivity. Polymers, like plastics, are long chains of repeating units connected by covalent bonds, making them versatile materials with a wide range of uses. We'll explore these structures in more detail in upcoming lessons. With molecules that have a not-so-small number of atoms, it is often helpful to write a formula that gives the simplest ratio of atoms, called an empirical formula. To understand this, let's look at an example. Consider glucose, which has the molecular formula C6H12O6. The ratio of carbon to hydrogen to oxygen atoms in this molecule is 6 to 12 to 6, which can be simplified to 1 to 2 to 1 by dividing by 6. Thus, glucose has the empirical formula CH2O. It is important to note that empirical formulae do not uniquely identify an element. For example, ethene and propene have the molecular formulae C2H4 and C3H6 respectively. They are unique compounds, consisting of different numbers of carbon and hydrogen atoms. However, they both have the same empirical formula, CH2, since the ratio of carbon to hydrogen in both of these compounds is 1 to 2. Through these examples, we see how covalent bonding plays a crucial role in the formation and properties of different substances. Understanding these bond formations and their strengths allows us to comprehend the molecular world. Before we conclude, let's consider the historical development of covalent bonds as an extension task. The concept of covalent bonds, where atoms share electrons, was first proposed by Gilbert N. Lewis in 1916. Lewis introduced the idea of electron pairs and the famous Lewis dot structures to visually represent how atoms bond. This groundbreaking work laid the foundation for our understanding of chemical bonding. Later, Linus Pauling expanded on these ideas and explored the nature of chemical bonds in more detail. Pauling studied how atoms interact and form bonds, leading to a deeper understanding of molecular structures. His influential book, The Nature of the Chemical Bond, published in 1939, summarized his findings and theories. Pauling's contributions to chemistry earned him the Nobel Prize in Chemistry in 1954. His work revolutionized the way we understand chemical reactions and molecular structures. In today's lesson, we explored covalent bonds, understanding how atoms share pairs of electrons to achieve stability. We examined examples such as hydrogen gas, H2, oxygen gas, O2, and methane, CH4, to illustrate single, double, and triple covalent bonds. We also briefly introduced the concepts of giant covalent structures and polymers. Understanding covalent bonds is fundamental to wider chemistry because they form the basis of molecular compounds, influencing their structure, properties, and interactions. In upcoming lessons, we will explore exactly how these covalent bonds influence the properties of substances, providing a deeper insight into the behavior of different materials and their applications in everyday life.